Hello everyone, I am Mudit Saxena, working as an assistant professor in the Department of Electronics and Communication Engineering, ABES Engineering College, Ghaziabad. Today we are going to discuss the topic combinational clippers. Combinational clippers are also known as bidirectional clipper or double-ended clipper. These are the contents of my presentation. So, what exactly the clippers are that we have already discussed in my previous videos. But for those who have not seen my previous videos, clippers are nothing but it is an important application of the PN junction diode, wherein clippers are used to clip either positive half cycle, negative half cycle, or a portion of it. Combinational clipper are the special case of parallel clippers. In case of combinational clippers, both positive as well as negative half cycles are clipped off depending upon the value of transition voltage. Now let's come to the classification of clippers. Clippers are broadly classified into two categories, unbiased and biased clippers. Unbiased clippers are those where only input voltage is given, no external battery is connected. Whereas in biased clippers, along with the input voltage, external battery is also connected in the given circuit. Unbiased clippers are of two types, series and parallel. Similarly, biased clippers are also of two types, series and parallel. So, bidirectional clipper is a special category of biased parallel clipper. Now let's do some problem based on the bidirectional clipper. So this is the numerical based on bidirectional clipper. So here you can see in the diagram, there are two branches and each branch comprises of diode and battery. So the first branch AB comprises of diode D1 and battery having magnitude of 5 volts, and the second branch, which is denoted by CD, this branch comprises of diode D2 and having a battery of magnitude 3 volts. So this is a standard circuit. In this circuit, we cannot change the polarity of the battery as well as the direction of the diode. This is a standard circuit of bidirectional clipper. So in this circuit, we need to draw the output waveform, or we can calculate, or we can also say that we need to calculate the V0. So in this circuit, the input voltage is sinusoidal, which is having magnitude of 10 volts. So first of all, we will draw the input voltage. So here we can see I have drawn the input voltage, which is sinusoidal and which is having magnitude of plus 10 and minus 10 volts. Okay, so this is the first step. Now, in step number 1, first we need to calculate the V0 during positive half cycle. So during positive half cycle, this will be plus and this will be minus. So here we need to check whether diode D1 is forward biased or reverse biased. Similarly, diode D2 will be forward or reverse biased. So we need to check the position of diode D1 and D2, whether they will be forward biased or reverse biased. So as we also know, during parallel clippers, only VI decides whether diode is forward biased or reverse biased, because the value of VI is always greater than the battery voltage. So here VI will decide, so the positive terminal of the input voltage is connected to the positive terminal of the diode D1. So diode D1 will be forward biased, and the same I have written here. And positive terminal of VI is connected to the negative terminal of diode D2. Therefore, diode D2 will be reverse biased. The same I have written here. So diode D1 will be forward biased. It means diode D1 will behave like a short circuit and diode D2 will behave like open circuit because it is reverse biased. So the resultant diagram will be like this. This is the resultant diagram wherein I have omitted the branch comprising of diode D2, because during positive half cycle, diode D2 will be reverse biased and it will behave like open circuit. So I have omitted this CD branch. So the resultant diagram will be this. So here we can see this is a circuit of parallel clipper. Why is it quad parallel clipper? Because diode and RL both are connected in parallel. So now here we need to find the transition voltage for this positive half cycle. As we all know, transition voltage, the magnitude of transition voltage is equal to battery voltage. So here in figure 1, the battery voltage is 5 volts. Therefore, transition voltage will be equal to 5 volts. Now we need to draw this transition voltage. So here we can see in the input waveform, this red dotted line is the transition voltage whose magnitude is equal to 5 volts. So this transition voltage cuts the positive half cycle of the input voltage at two places, here and here. So we can say this transition voltage divides the positive half cycle into three parts: 0 to 1, 1 to 2, and 2 to 3. So positive half cycle is divided into three parts. So now, while calculating the V naught during positive half cycle, we have considered three cases. Case 1 corresponds to the portion between point 0 to 1. Case number 2 correspond to the portion between point 1 and 2. And case number 3, this case correspond to the portion between point 2 and point 3. So let's start with the case number 1. So in case number 1, I have written Vi less than 5 volts. The same can be seen in the input waveform. Here we can see the input voltage is less than the transition voltage, which is shown by the dotted line. Now, how do we calculate V naught? So here, whichever is higher, that is going to decide whether diode will be forward biased or reverse biased. So in case number 1, 5 volt is greater than as compared to Vi. So this 5 volt battery will decide whether diode will be forward biased or reverse biased. So here we can see the positive terminal of the battery is connected to the negative terminal of the diode. Therefore, this battery will make the diode reverse biased. And the same I have written here. And when the diode will behave like reverse biased, it will behave like open circuit. So the output voltage will be equal to the voltage across RL, and the same will be equal to Vi. It means whatever the input voltage is, the same we will get the output voltage, both in magnitude as well as in shape. So in case number 1, we will draw the output voltage. So these two lines correspond to case number 1. These two lines correspond to case number 2, and these two lines correspond to case number 3. So these two for case number 1, this 2 for case number 2, and these two lines correspond to case number 3. So in case 1, V naught is equal to Vi. So here we can see during case number 1, input starts from 0 and it is going up to 5 volts. So the same will be the output. It is starting from 0 and going up to 5 volts. So this is the output during case number 1. Now let's take case number 2. In case number 2, Vi is greater than 5 volts. That means now the input voltage is going to decide whether diode will be forward biased or reverse biased. So during case number 2, because case 1, case 2, and case 3, all three cases comes under the positive half cycle. So this will be plus and this will be minus. So case number 2, Vi will decide So the positive terminal of Vi is connected to the positive terminal of diode D1. Therefore, this input voltage will make the diode forward biased. And the same I have written here in case number 2. And as we know, when the diode is forward biased, it will behave like short circuit. So it will behave like short circuit. So the circuit will be like this. So now the V0 will be equal to voltage across RL, and the same will be equal to voltage between point A and B. And the voltage between point A and B will be equal to 5 volts, which is equal to transition voltage. So the same I have written here. During case number 2, V0 is equal to constant 5 volts. So here I will draw the output during case number 2. So the case number during case number 2 output is equal to 5 volts. So this is the output correspond to case number 2. Now let's come to the case number 3. Case number 3 and case number 1 both are similar. So in case number 3, diode V1, Vi will be less than 5 volts and the diode will be reverse biased as we discussed in case number 1. So therefore, V0 will also be equal to Vi. So let's see how the Vi is during case number 3. So if we see the positive half cycle, so during case number 3, which correspond to portion between point 2 and 3. So here we can see during case number 3, the output starts from 5 volts and it is ending at 0 volts. So the same will be the output. The output will start from 5 and it will end at 0 volts. So this is the output of case number 3. So this is the output of complete positive half cycle. Now, let's calculate the output during negative half cycle, which is shaded by the green lines. So in step number 2, we are going to calculate V0 during negative half cycle. So during negative half cycle, the sign will be changed. This will be minus and this will be plus. Now the negative terminal of Vi is connected to the positive terminal of D1. Therefore, D1 will be reverse biased. And the negative terminal of Vi is connected to the negative terminal of diode D2. Therefore, D2 will be forward biased. So during negative half cycle, D1 is reverse biased and D2 is forward biased. And the same I have written here. During negative half cycle, D1 is reverse biased and D2 is forward biased. And as we all know, the diode which is forward biased that will behave like short circuit and the diode which is reverse biased that will behave like open circuit. So the diode D1 will behave like open circuit. So let's omit this branch AB. So when we will omit this branch, the resultant diagram will be like this, which is shown in figure number 2. This is figure number 2. So in figure number 2, you can see I have omitted the branch which was comprising of diode D1. So this is the resultant circuit during negative half cycle. And again, this is a parallel clipper because diode and RL both are connected in parallel. Now, here also we will calculate the transition voltage. So here I have calculated the transition voltage. So as we all know, transition voltage is equal to the magnitude of battery voltage. Because in figure 2, the battery voltage is 3 volts. Therefore, transition voltage is also equal to 3 volts. Now, we need to check whether this transition voltage will be positive or negative. So, because the battery, in my earlier videos, I have already told in case of, in all the numericals of parallel clipper, the battery will be connected in 2 ways. If the battery is connected like this, and if its voltage is V, so the transition voltage will be positive. If the battery is connected like this, means negative terminal comes first, And if its voltage is V, so this will be taken as negative voltage. So in figure 2, because the negative terminal of battery comes first, therefore transition will be negative. So this is how we have calculated the transition voltage. So once the transition voltage is calculated, now we need to mark it on the output in the input waveform. So because the transition voltage is -3, so this is also shown by the red dotted lines during negative half cycle. So this is the transition voltage, -3 volts. Okay. So this -3 volt transition voltage again cuts the negative half cycle at two places. This is first point and this is second point. So we can see the negative half cycle is again divided into three parts. First part 3 to 4. Second part correspond to point number between point number 4 and 5, and the third part correspond to the points between 5 and 6. So the negative half cycle is again divided into three parts. First part correspond to portion between 3 and 4. Second part corresponds to the portion between point 4 and 5, and the third part corresponds to the portion between point 5 and 6. So while calculating the V naught during negative half cycle, we will consider three cases: case 1, case 2, and case 3, as we took these three cases in the forward in the positive half cycle. So here also, in case number 1, we can see Vi is less than 3 volts, as you can see in the input waveform. So case number 1 correspond to the portion between point 3 and 4. Case number 2 correspond to the portion between point 4 and 5. So here we can see the input voltage exceeds the transition voltage, which is -3 volts. So in case 2, Vi will be greater than 3 volts. And in case number 3, Vi is less than 3 volts. So the same can be seen in the input waveform. So in case 3, you can see the input goes below the transition voltage line, which is -3 volts. Okay. So these are the three cases. So let's take all three cases one by one. So let's take case number 1 first. So here 3 volt is greater than Vi. So 3 volt means battery voltage. So the battery voltage is going to decide whether diode will be forward biased or reverse biased. So we can see the negative terminal of diode battery is connected to the positive terminal of diode. So therefore, this battery will make the diode reverse biased, and the same I have written in case number 1. And when the diode is reverse biased, it will behave like open circuit. So the circuit will be like this. So it will behave like open circuit. So V naught will be equal to the voltage across RL, and the same will be equal to voltage between these 2 points. Which is equal to Vi. So here we can see during case number 1, V naught is equal to Vi. Whatever the input is, the same will be the output, both in magnitude as well as in shape. So during case number 1, the input starts from 3, which is at 0 potential, and it is going up to at point number 4, which is at -3 volts. So the output will be like this. It will start from 0 if it is -3 volt. So the output will go up to -3 volt. So this is the output during case number 1. Now let's take case number 2, where Vi is greater than 3 volt. That means input is going to decide whether diode will be forward biased or reverse biased. So let's put the diode here. Okay, so here, because this is negative half cycle, so this will be minus and this will be plus. So here VI is going to decide whether diode will be forward or reverse biased. So here we can see the negative terminal of VI is connected to the negative terminal of the diode. Therefore, this VI will make the diode reverse forward biased. So the same I have written here, diode will be forward biased. And when the diode is forward biased, it will behave like short circuit. So the resultant circuit will be like this. So here V naught will be equal to voltage across this RL, and the same will be equal to the voltage between point 1 and 2. So the voltage between point 1 and 2 is equal to minus 3 volts. So here the same I have written. The V naught will be equal to minus 3 volts. Okay. So I need to draw this output voltage. So during case number 2, so case number 2 corresponds to the portion between 0.4 and 5. So during case number 2, the output is minus 3 volt. Minus 3. This is the output of case number 2. Now let's discuss case number 3. Case number 3 and case number 1 both are same. So in case number 3 also, diode will be reverse biased. The same we have discussed in case number 1. And the output voltage will be equal to VI. So let's see how the VI is during case number 3. So during case number 3, the VI at 0.5 is minus 3 volt, and it is ending at point number 6. That means at 0 volts. So the input starts at minus 3 volt and ends at 0 volts. So the same will be the output. The output will start at minus 3 volt and it will end at, sorry, let me draw it again. So it will start from minus 3 and will end at 0 volt. So this is the output of case number 3. So this is all about the output during negative half cycle. So here we can see whether it is a positive half cycle or negative half cycle. Both positive and negative half cycles are clipped off. So if we see the input waveform, so this portion of positive half cycle is clipped off and this portion of negative half cycle is clipped off. Therefore, we can say this is an example of bidirectional clipper, which is also known as double-ended clipper, or it is also known as bidirectional clipper, double-ended clipper, and combinational clipper. So this is all about bidirectional clipper. Thank you.